Hello friends, in class 12th the P block elements group 18 elements, and in this video we will discuss about xenon-fluorine compounds, their preparation and structure, and xenon-oxygen compounds, their preparation and structures. First come to the xenon-fluorine compounds preparation. Xenon forms three binary fluorides XeF2 xenon difluoride, XeF4 xenon tetrafluoride, XeF6 xenon hexafluoride by the direct reaction of elements under appropriate experimental conditions. From these reactions you can see when xenon is in excess and when react with the fluorine at these conditions it will form XeF2. When xenon and fluorine are in 1:5 ratio, in these conditions, they will convert into XeF4. And when xenon and fluorine are in 1:20 ratio, under these conditions, they will convert into XeF2. Xenon hexafluoride can also be prepared by the interaction of XeF4 and O2F2. Okay, this reaction represents this one. Properties of xenon-fluorine compounds. XeF2, XeF4 and XeF6 are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, XeF2 is hydrolyzed to give XeHF and O2 according to this reaction. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. Okay, you can see from this equation like XeF2 when react with PF5. Actually, in this case, this PF5 is a fluoride ion acceptor. That's why it accepts the electron and this will convert into the negatively charged species, while XeF2 lose one fluorine and convert into cationic species XeF positive charge, one positive charge. The same way, XeF4 when react with the SbF5, this XeF4 lose one fluoride ion and this fluoride ion is accepted by this SbF5 and this species is formed. XeF3 positive charge, SbF6 negative charge. But when XeF6 react with the MF metal fluoride, where M may be sodium, potassium, rubidium or cesium, and in that case this MF is a fluoride donor. And that fluoride is accepted by the XeF6 and this XeF6 will convert into XeF7, one negative charge. That is anionic species will form. Structure. This again one of the important part of this group 18 elements. Structure of xenon-fluorine compounds. So we can determine the structure either by VSEPR theory or by hybrid state of the central atom. Okay, in both the cases we have to find out the total number of electron pairs, and this total number of electrons pair will be equal to number of hybrid orbitals in these cases. Okay, and these can be found out by using this formula: half of the number of valence electron in free atom plus number of monovalent surrounding atoms. Monovalent means atoms or elements having valency 1, and free atom means not in bonded form, in elemental form. Okay, now let us see one by one. XeF2, if we apply this formula, in case of xenon, valency electrons are 8 and monovalent surrounding atoms are 2. How can we find out this 2? That is these fluorine are 2 and fluorine is a monovalent atom, and half of it, if we divide by 2, then this will be equal to 5. Total number of electron pairs are 5, or we can say hybrid orbitals are 5. That's why hybridization is sp3d. But out of these 5 electron pair, 2 are bond pair. How can we decide that 2 are bond pair? Because xenon is surrounded by the 2 fluorine atoms. That's why bond pair of electron are 2 and remaining 3 are the lone pair of electron. That's why these 5 electron pairs are arranged in trigonal bipyramidal manner, but due to the presence of 3 lone pair of electron, its geometry becomes linear like this structure. These are the 2 bond pair of electrons and these are the 3 lone pair of electrons. Clear, student? Now come to this XeF4. In the same way we can find out this, that is 8 plus 4 and this is divided by 2 and this will come 6. Total number of electron pair are 6, or we can say number of hybrid orbital are 6. That's why hybridization is sp3d2 and these hybrid orbitals are arranged in octahedral manner. But out of these 6 electron pair, 4 are bond pair and 2 are lone pair. That's why geometry becomes square planar. You can see this diagram. Okay, this is one lone pair is above the plane and one lone pair is below the plane. XeF6. In the same way you can find out that is 8 plus 6 divided by 2 and this will become is equal to 7. Total number of electron pair are 7, or we can say number of hybrid orbital are 7. That's why hybridization is sp3d3 and these 7 hybrid orbitals are arranged in pentagonal bipyramidal manner, but there is a one lone pair of electron. Again, how can we find out that bond pair and lone pair? This xenon is surrounded by the 6 fluoride ions. That's why 6 bond pair and 1 is a lone pair. That's why geometry becomes a distorted octahedral. Okay. Now come to the xenon-oxygen compounds. Hydrolysis of XeF4 and XeF6 with water gives XeO3. Now you can say when this XeF4 is hydrolyzed, this will give XeO3, and when XeF6 completely hydrolyzed, then this will again give XeO3. But when XeF6 undergo partial hydrolysis, then it may give XeOF4 and XeO2F2. See, if one water molecule is there, it will convert into XeOF4. If 2 water molecules are used for the hydrolysis, this will convert into XeO2F2. Now again, structure of xenon-oxygen compound. In this case, we will find out the structure by using the hybridization of the central atom. And again, we first will find out the number of hybrid orbitals using the formula which we discussed we have discussed already. That is half of the number of valence electron in free atom plus number of monovalent surrounding atoms. Now see one by one. This is XeO3. Now in this case, this oxygen is a divalent. It is not a monovalent. And this xenon, it have 8 valence electrons in free state. That's why this is 8 plus 0. No monovalent atom is there. Divide by 2. And this will be equal to 4. It means we can say number of hybrid orbitals are 4. That's why hybridization is sp3. And these sp3 hybrid orbitals are arranged in tetrahedral manner. Okay, but again we can say in case of tetrahedral manner, there are the 3 oxygen atom will make a sigma bond using 3 sp3 hybrid orbital. Okay, and one hybrid orbital will occupy one lone pair of electron. That's why its geometry becomes pyramidal. This is the geometry of XeO3. At the same time, oxygen is a divalent. That's why oxygen also form one pi bond with n hybrid p orbitals. Okay. Come to XeOF4. In this case, this is divalent, but fluorine is a monovalent. That's why we can say this is 8 plus 4, and this is divided by 2, and this will be equal to 6. 6 hybrid orbitals. That's why hybridization is sp3d2. They are arranged in octahedral manner, but again we can say that the total number of sigma bonds formed by these hybrid orbitals are 5. Okay, that's why their geometry becomes square pyramidal. You can say this is one lone pair of electron, and this out of these double bond, one is sigma and one is pi. Sigma bond is formed by the hybrid sp3d2 orbital, and one pi bond is formed by the unhybrid p orbital. The same case, this is XeO2F2. We can find out that is 8 plus 2. Why only 2? Because oxygen is a divalent and this is divided by 2 and this will come 5. Total number of hybrid orbitals are 5. sp3d is the hybridization. These orbitals are arranged in a trigonal bipyramidal manner, but only 4 hybrid orbitals will make sigma bonds and there is a one lone pair of electron. That's why geometry becomes this is seesaw. Okay, so we can say this XeO3 is a colorless explosive solid and has a pyramidal molecular structure. XeOF4 is a colorless volatile liquid, has a square pyramidal molecular structure, and XeO2F2 has seesaw structure. Okay student, subscribe my channel for the new video. Thank you.